All right, so last class we had very brief introduction to hypothesis testing, okay? And I understand that most of you, or just about all of you, have learned about hypothesis testing before. So I'm going to be very brief and quick about this subject so that we can go on to a more interesting topic of regression, right, as quickly as possible, okay? All right, so hypothesis testing, again, we're trying to make a guess on the unknown population parameter based on some sample statistic, okay? And there are two different ways, interval estimation and point estimation, okay? Interval estimation was about the confidence interval, okay? And the point estimation is hypothesis testing. So we start out with the null and alternative hypothesis. All right. So here's some, I guess it's an example. Okay? So in this example, somebody claims that the population mean age is 50. Then we set it up as null hypothesis. And throughout the test, we are going to assume that this null hypothesis is true, okay? Until we find sufficient evidence to reject this null hypothesis. Okay? So alternative hypothesis says it is not true, it is not 50. Okay? And then we're going to take some sample. Okay? And here I need to remind you guys of the concept of sampling distribution. Okay? So again, we have population, okay? And there is unknown parameter, probably mean, okay? Population mean. Okay? But since population is usually too large and just too expensive and too time consuming to process all the observations in population, we take small sample, okay, and then calculate the sample statistic, okay, and then we're going to make a guess on the population mean based on the sample mean, okay. Well, what we need to do here is we need to think about some distribution of sample means or sample statistic. Because, we are taking a very small portion of the entire population, okay? So depending on how you select the sample, first time you select suppose the population size is, say, 1 million. You have 1 million observation in population, right? And you are taking a small sample, say, 100 observations out of the entire 1 million observation in the population, right? So every time you take a small sample, another sample of 100 observation, right? These sample mean can come out differently, right? You can understand that situation, right? Because you are randomly selecting these 100 observations out of 1 million observation, okay? So we can think about some distribution of sample means. Okay? Sometimes you may get a little bit small number for the sample mean. Next time you take another sample, you may get quite different number, and so on, right? Right? So that's what we call sampling distribution. Okay? Sampling distribution. So sampling distribution is distribution of sample statistic. Okay? Again, sample statistic could be mean or standard deviation or proportion, something like that, right? Whatever represent the unknown population parameter, population mean, population standard deviation or population proportion, and so on. Okay? So we can think about the distribution of sample means, which we call sampling distribution. Okay? Can you hear me all right from the back? Is this microphone working? Okay, good. All right. And then there is what we call CLT, What is CLT? Remember? Summer was too long, I guess. Yeah? Just central limit theorem. Central limit theorem. Okay? You remember what it is about?
Something like the sample size is more larger. The sample statistic is approach to the normal distribution.
Yeah, right. So CLT, central limit theorem, this is a very important theorem, right? Without CLT, the statistic cannot exist, almost. Okay? Because this population, the problem with population is just too large, okay? And it is unknown. So we don't know the actual distribution of population. I don't know, whether population is normally shaped, or it has some weird, twin peak shape, or some, very strange distribution. We have no idea what the population looks like, right? But CLT says, central limit theorem says, as long as you select sufficiently large sample, right? The sampling distribution, in other words, the distribution of sample statistic will have a normal distribution. Okay? So as long as you select a sufficiently large sample, we don't need to know the actual distribution of population, right? Because the sampling distribution will be, you can assume it to be normal. Okay? All right, so when you have the normal distribution, we have many convenience or advantage, because we know a lot about the normal distribution. Okay? And for example, if you have, if this is considered normal, right? You can convert this sampling distribution into standard normal distribution, what we call Z distribution. Okay? And everything is known about the Z distribution, right? So, if you have if this is the mean value, center of the Z distribution is centered at 0, right? Again, I'm going very quickly, so if you have any trouble, let me know. I'll be happy to explain to you individually. Okay? So whatever the variable is normally distributed, we can convert it into Z distribution by subtracting mean value and dividing with the sigma or S, right? Standard. If we are dealing with the sample, I guess you can say sample standard deviation. Okay. Okay. So in that case, whatever, if this is the mean value, okay, then we can convert it into 0. Okay. And if you have one standard deviation from the mean, then it's going to have what? You still remember? Between I'm going a little too fast here. Okay? So, if the sample standard deviation is S, then the standard deviation of the sampling distribution will be S divided by square root of N, right? All right, so you have to do that, right? And then between -1 and +1 on Z-score, which means this difference between actual number and the center is exactly 1 times the standard error. This is what we call standard error. Okay? So between -1 standard error and +1 standard error, we're going to have what? You remember? What percentage of all the observations? Roughly? 68, right? About 68, yeah, about 68% of all the observation, right? Between 2 standard deviation, right? About 95%, right? Within 3 standard deviation from the mean, what? 99.7%, in other words, almost 100%, right? Almost 100% of observation will be found within 3 standard deviation, right? So, we have the, what we call Z table, okay? And Z table gives us exact proportion, exact probability, right? Depending on, the number of Z score. If you have 1.28, for example, right? What will be this area? We can find out exactly, right? So, that's why I say, having the central limit theorem makes our life a lot easier, right? And it makes actually the statistical analysis possible, okay? Because we can convert whatever variable, normal variable, into standard normal, and we can find all the answers that we want, okay? All right, anyway, so here, it's the situation. The example here is we have distribution of x bar, which means this is the sampling distribution of sample means. Okay? And null hypothesis claims it is centered at 50, right? In other words, the population mean is 50. Okay? And then suppose you took a sample, okay? And actually calculated the sample mean, right? And for some reason, sample mean came out to be 20, right? Then you can think about the question, how likely is it? If actual population mean is actually 50, right? When you took a sample, right? My sample indicates the sample mean is 20, right? Isn't it just too far away, right? What do you think? So based on this, can we reject the null hypothesis? In other words, can you say that null hypothesis claiming the population mean is 50 is not correct because my sample indicates mean is 20?
Depends on how you fix alpha error.
Depends on what? How you what?
How you fix your alpha. But it's probably unlikely that the mean will be 20.
Oh, you mean alpha value? Did you say?
Like the confidence.
Oh, okay. Yeah. How we fix alpha value? Right. Okay. Right. So yeah, that is right. So there are 2 possibilities here, right? So if you have this result, the first thing we can think of is, well, the null hypothesis is wrong, okay? That the claim that the population mean is 50 is not true because my sample just indicates too much difference, right? Different result, okay? That's one possibility. What's the other possibility? What if that null hypothesis is still true? It is actually true, but what? What could have happened? What? Come on. Any other possibility? Huh? Oh, type 2 error. I think you're going a little too advanced, too fast. Okay? Well, can't you think? Don't you think you could have made an error? In other words, when you selected the sample, somehow you selected a bad sample, right? It is possible, right? Because you're selecting a random sample, right? So out of million people in the population, right? Somehow, when you selected your sample, you selected only very young people into your sample. It could happen by chance, right? Of course, you probably did not intend that way, right? But it is possible, yeah? So there are two possibilities. One possibility is if the sample is good, then the null hypothesis is not true. It is incorrect, right? Second possibility is null hypothesis is still true, but somehow you selected a bad sample, right? What do we mean by bad sample? In other words, whatever, if your sample does not correctly represent the population, that's a bad sample, right? I mean, there are many different ways you can select a bad sample, right? But you know, in short, if your sample does not represent the population, that's a bad sample, right? So there are two possibilities here, right? Okay, so what can we do? Well, practically, if your sample mean is close to the assumed population mean, excuse me. So assumed population mean is what the null hypothesis claims, okay? Then, well, you have no reason to reject the null hypothesis. You cannot reject the null hypothesis, right? If the sample mean is far from the assumed population, then you'll probably have to reject the null hypothesis, right? So in your sampling distribution, right, your null hypothesis claims the mean is 50, but here you got sampling sample mean came out to be 20, right? Then in all likelihood, you'll probably have to reject the null hypothesis, right? But the question is, well, how far is far enough, right, to reject the null hypothesis? What if the sample mean came out to be 35? Should we reject the null hypothesis or not, right? So for that reason, we have to come up with a critical value, what we call critical value of a test statistic. Okay? Well, first of all, what is the test statistic? Depending on what situation you are in, you can use either Z or T as your test statistic, right? Z is used only when sigma is known. In other words, if somehow you know the population standard deviation, right, then you can use Z score as the test statistic, right? Otherwise, you'll have to use T. Okay? Yeah, about the details of the test statistic, it'll come in a few minutes later, right? So, you know, in short, I guess at this moment you can see this is very unlikely because, you know, the whole situation that we are in right now, what we're trying to find out is we're trying to make a guess on the population mean because we don't know the population mean, right? But how do you calculate the population standard deviation? You still remember this formula? Huh? Population standard is, the concept of standard deviation, of course, is dispersion, right? How widely the data points are scattered, right? So what we do is we calculate from each observation we subtract the population mean and add them up. Add up all these, before we add up, we square those distances, right, differences, right? And then divide the whole thing by the population number of observation, right? That's the formula for sigma, right? Or population standard deviation, right? But if we don't know the population mean, how are you going to calculate the population standard deviation, right? It is highly unlikely that you will actually know sigma if you don't know mu, right? Okay? So this, I can tell you, this situation is just you will encounter within statistics class, right? Only within the theory, right? In reality, you will almost never use the z distribution, right? Most of the, I would say 99.9% of the tests that the actual researchers run, right, are based on t-test, okay? T distribution. Okay. I'll introduce the t distribution later. Excuse me. All right. So to understand how we come up with the critical value, we have to understand the types of error. The two types of error. Okay. So here on the columns, we have actual situation. Either HO, the null hypothesis, could be true or false, right? On the row-wise here, we have our decision, right? Accept the null hypothesis, reject the null hypothesis, right? So if the null hypothesis is true, then accepting is the right decision or correct decision, right? If the null hypothesis is false, then rejecting it is the correct decision. The other two cases are error, right? And we call this type 1 error, we call this type 2 error, right? So what is type 1 error? Can you verbalize it? What's the concept of type 1 error? It's the error of go ahead.
When you get a bad sample, you have a type 1 error, for example, in that case.
Okay, right. But what I'm asking here is just based on this table, I'm asking the definition. It's the error of rejecting the null hypothesis when in fact, what? It is true, right? If you reject the null hypothesis when in fact it is true, that's type 1 error, right? The other error, type 2 error, is error of accepting the null hypothesis when it is in fact false, right? So there are two different types of errors, right? So type 1 error is error of rejecting the null hypothesis when it is in fact true. So going back to our example, right? Even though we got this result, right? Our sample indicates that the population mean is actually 20, right? It is possible that this is still true, right? But because your sample result was just too far away from the null hypothesis, if you decide to reject the null hypothesis, right? So here's okay. Because your sample result was just too far away, which makes your test statistic too large, right? You know, is whatever 20 minus 50 divided by, you know, s over square root of n, right? Whatever you calculate it that way, right? Actually, this should be sigma because we are using z statistic, right? Anyway, so when you have this large distance, you're going to have large test statistic in terms of absolute value, right? So if it's when you convert it this into a z-score, it may come out to be negative 2.5 or something, right? Which is far away from 0, right? Then you may have to reject the null hypothesis, right? However, you could be still making an error. In other words, as you said, if your sample was bad, right? Somehow you selected a bad sample and sample does not represent the population, right? Then it is still possible that population mean is actually 50, but somehow you decided to reject the null hypothesis, right? That's type 1 error, right? Well, we can control the risk of type 1 error, right? By setting up alpha level, right? Okay. Okay. Alpha, the name of alpha or definition of alpha is level of significance or significance level, right? And this is actually probability for type 1 error. Probability for type 1 error. Okay? So what we are going to do is on this z distribution or the distribution of the test statistic, okay? Here's the center. On z distribution, of course, it is 0, right? The standard normal distribution center is 0 and the standard deviation is 1, right? And we're going to just set up what we call rejection region. Rejection region, right? On both sides. Okay? And if our test statistic falls within the rejection region, like this, right? Then, because our test statistic is too far away from 0, which means our sample mean was just too far away from hypothesized value, right? We will decide to reject the null hypothesis, right? So this, in effect, becomes critical value. Okay? So critical value is the value which separates rejection region from non-rejection region. Okay? And how do we set up that critical value? Well, it depends on what percentage or what probability we allow for type 1 error. Why do we have to allow? Why do you have to allow for error? I mean, can you just completely eliminate the error? Why not? Why do we have to accept some percentage for error? Is there any way we can eliminate completely the probability of error? What? Make the sample size equal to population size, in other words, right? If you just use entire population in your analysis, yeah, then you can, of course, eliminate possibility of error. There is no error because you use the entire population, right? In other words, you know exactly what the population mean is. There cannot be any error, right? Right? That's the only way, right? So in other words, I mean, we are doing this statistic just because we cannot do that, right? If you can use entire population in your analysis, you don't need the statistics. All you need is a calculator. Just add them up and divide by population size, right? And that will be 100% accurate, no error, right? But we need statistics because we can't do that, right? All right. So the fact of life is there is no way you cannot eliminate the probability of error. You have to accept, you have to allow at least some percentage, right, for error, right? For this type 1 error, it's up to you. What probability are you willing to allow for type 1 error, right? For some reason, if you can allow large error for type 1 error, right, then you can come up with small critical value or critical value which is close to 0 or center, right? Then, this area outside the critical value, that becomes alpha, right? Or actually half of alpha, because you're going to allow the same size on the other side. So here's half of alpha, right? So, for example, if you are willing to allow 10% for type 1 error, right? Then you're going to allow 0.05 on each side, right? Right? And anytime your test statistic falls within the rejection region, in other words, anytime your test statistic exceeds the critical value on either side, right? You're going to reject the null hypothesis. That's your decision rule, right? But you have to understand that there is a still probability of error. You may be committing an error, right? So that's the concept of level of significance, okay? And type 1 error and the critical value. And that's how you make the decision in hypothesis testing. Okay? Well, what if your test statistic actually came here? Then what is your decision? Right? What is your decision? Hyunwoo? What is your decision? You're thinking of something else, right? Well, this is a non-rejection region, right? Okay? So if your test statistic falls there, then your conclusion should be what?
Not reject.
Do not reject, right? What can we accept?
Sorry.
What can't we accept the null hypothesis?
There is still a chance to make a type 2.
Right. Very good, right? So yes, if the test statistic comes in here, then it's pretty close to the hypothesized value, right? So you do not have reason or sufficient evidence to reject this null hypothesis, right? In other words, actually you can say your evidence supports the null hypothesis, right? But then what can't you say just accept the null hypothesis, right? Well, because we are not certain. In other words, even though the evidence suggests that the null hypothesis is true, there is still possibility that it may not be true, right? Because again, we are dealing with a sample, right? So if you say accept the null hypothesis, then you are risking the possibility of type 2 error. Type 2 error is an error of accepting null hypothesis when in fact it is not true, it is false, right? Well, unfortunately, there's nothing we can do. I mean, as far as type 1 error goes, we took care of it by setting up the alpha value. So whenever you run the test, you know exactly what, how much error, how much risk of error you are taking for type 1 error, right? Because we have set up, 0.05 or point of whatever you want. But as far as type 2 error goes, we have no idea how much risk we are taking, right? So at this introductory level, right, of statistics, our recommendation is just say, if you cannot reject it, just say cannot reject it or do not reject the null hypothesis. You never say accept, right? That way you can avoid the probability of type 2 error, right? But if you think about it, that doesn't make any sense, does it? Right? I mean, think about it. In actual situation, suppose you are producing some products, say. Many times we use the bottling example, right? Suppose you're running a Coca-Cola bottling plant, okay? And each can should include exactly what? 12 ounces of Coca-Cola, right? So every hour or so, if you are a quality control manager, you should take some sample and actually measure the amount of liquid inside the bottle, right? And to check whether the machine is working fine or not, right? So your setup null hypothesis, mean is 12 ounces versus mean is not 12 ounces, right? Either way, I mean, if it's too much or too little, that's a problem, right? So if you have sufficient evidence to reject this null hypothesis, then what are you going to do? Suppose you took some sample and measured the amount of liquid inside the bottle, right? And it was far away from 12 ounces, either too much or too little, right? What are you going to do? What is the action you should take? Huh? Call the engineer, right? To stop the machine, right? And check the machine and possibly adjust the machine because apparently your machine is malfunctioning, right? So if you can reject the null hypothesis, then the correct action is stop the assembly line or whatever, stop the machine, right? And check and adjust, right? But what if you cannot reject the null hypothesis? Your conclusion is do not reject the null hypothesis. What is your action? What are you going to do? I mean, yeah, you can say whatever you want, but the conclusion is do not reject the null hypothesis, right? So what is your action? What is the course of action to take? Go back to sleep? Right? What are you going to do? Huh? Right. Continue production, right? You're not going to stop the machine, right? Which means you are actually accepting the null hypothesis, right? If you continue your production, you are saying, okay, machine is fine, right? Machine is doing what it's supposed to do, right? So there is no difference in reality, right? In reality, there's no difference between not accepting, not rejecting it and accepting it, right? There is no difference in reality, right? But in statistics course, only in this course, right? You cannot say accept it. Because if you say accept it, then you're risking a chance of type 2 error. Okay? All right? Okay, so we've talked about all these things, all right? Type 1 error, type 2 error, right? Okay, so here, the probability of type 2 error is beta, right? Which depends on alpha value and the sample size, right? So there is a kind of a trade-off between alpha and beta, right? So dealing with the probability of type 2 error requires a little more advanced statistical knowledge, right? So we're not going to deal with here, right? So in this course, you just avoid committing type 2 error by not saying accept, right? Just say do not reject if you cannot reject it, right? All right. So here, we talked about the hypothesis testing, concept of hypothesis testing, right? So if the sigma is known, then you can run the z-test, right? And you calculate the z statistic this way, okay, right? If the sigma is known, right? And based on this, this is what we call test statistic, right? And based on the location of the test statistic, you can either reject the null hypothesis or do not reject the null hypothesis, make a conclusion, okay? Right? So here, what I just explained here is what we call critical value approach to testing, right? So depending on the alpha level, you set up the critical value, right? And by comparing your test statistic to the critical value, you can make the decision, right? All right? So the steps are, but there are two-tailed test and one-tailed test, okay? So far, I've been dealing with the two-tailed test, but sometimes you want to run the one-tailed test, right? I think last class I used the example of Hyundai Kia gas mileage example, right? There, Hyundai and Kia, claimed that their average gas mileage is at least 40 miles per gallon, okay? But the researchers at EPA, Environmental Protection Agency, right? They claimed that actual gas mileage was less than 40, right? So this is the one-tailed test, because we're talking about only one side, right? Okay. So what happens is you can convert the 40 into a z-score, right? And let's say suppose the actual gas mileage came out to be, say, 37, right? So those researchers at the EPA tested some cars, right? And they came out, on average, they were getting only 37 miles per gallon, right? So they converted into z-score. So 37 minus 40 divided by whatever, sigma over square root of n. And suppose that was 1.2, right? So negative 3 divided by 1.2 would be negative 2 point what? Would that be 2 point, let's say 2.7, right? Okay. So it came out to be negative 2.7 here. Test statistic came out to be negative 2.7, right? And that would be inside the rejection region, apparently, right? So whatever the alpha level they used, right? They probably used about 95% for alpha level of 0.05, right? So if you are running one-tailed test, then you can set up entire, suppose they want it to be 95% confident, right? About their conclusion, right? That means alpha level is 0.05, because what that means is they are allowing 5% probability for type 1 error, right? If you want to be 95% confident, okay? Then if you're running one-tailed test, you can allow entire 0.05 on one side. You don't have to distribute on both sides, right? And on the two-tailed test, if it were two-tailed test, then you would set up 0.025 here and 0.025 here, right? But if you're running one-tailed test like this, right? And all that matters is whether it's smaller than or not. You don't care whether it's greater than, right? So you will set up entire 0.05 or alpha level on one side, and you can make the decision, right? That's the only difference between two-tailed test and one-tailed test, right? On one-tailed test, you set up entire alpha level on one side, right? One tail, okay? Okay, anyway, so so this is what we did, right? So yeah, you can calculate the critical value, find the critical value from the table, Z table, and then calculate the test statistic and find out whether test statistic is inside the rejection region or not, okay? And then make the decision, okay? Okay, so here's another example of two-tailed test, okay? So in summary, we have 6 steps in hypothesis testing. So first step is you have to state the null and alternative hypothesis, right? Make sure you remember that equal sign only goes on what? Null hypothesis, right? Alternative hypothesis cannot have equal sign. So only the not equal sign or less than or greater than, right, can be on the alternative hypothesis, right? And then you choose the level of significance alpha and the sample size n, okay? So calculate the test statistic based on that. Determine the critical value based on alpha, okay? And calculate the actual test statistic based on the sample mean, right? And then you can make the decision, right? And yeah, so whenever you run the hypothesis testing, well, you have those 6 components, okay? Well, in your actual test, in my class, I usually give you this thing, right? Null, alternative spaces for null and alternative hypothesis, test statistic, right? And decision rule, and conclusion, and finally interpretation. Okay? So you have to have those 6 components, right? You have to state the null, alternative, test statistic, either Z or T. You have to show how you calculate the test statistic, right? And decision rule is reject the null hypothesis if something like that, right? Reject the null hypothesis if the absolute value of test statistic is greater than T of alpha with the degrees of freedom. T statistic has degrees of freedom, right? N minus 1, something like that, right? So in your actual situation, you may use 0.05 as your alpha level. Degrees of freedom may be 15, right? In case you have 16 as the sample size, something like that, right? All right. So you have to actually look for these numbers from the T table and say this is 1.27, something like that, right? So what that means is we have T distribution, and you found out, considering your alpha level and the degrees of freedom, your critical value, critical T happens to be negative 1.27 and 1.27. So you have rejection region here, right? So your decision rule is if your test statistic either positively or negatively exceeds this critical value, then you're going to reject the null hypothesis. Okay? Do you understand this decision rule, right? This is the case of two-tailed test. Okay? If you're running one-tailed test, you can be more specific, right? If you're running one-tailed test like this, right? Then obviously you're running lower tail test. This is called the lower tail. This is called the upper tail, right? So you can say reject the null hypothesis if the test statistic is less than T of 0.05 degrees of freedom 15 which is 1.2, negative 1.27, right? If you're running this lower tail test, right, then you can be this specific, right? You will reject the null hypothesis if your test statistic is less than negative t of 0.05 with the degrees of 15, which is negative 1.27, right? I'm just making up this number. I'm not sure what this number is, right? You can find it out from the t table, right? Okay, so that's the thing. And then the conclusion. Based on this, you can make the conclusion either reject the null hypothesis or do not reject the null hypothesis. Yeah? And finally, what does that mean? Right? So in case the conclusion came out to be reject the null hypothesis, right? In this situation, let's say, right? Then you can say we have sufficient evidence that Hyundai Kia cars have average gas mileage of less than 40 miles per gallon, right? So in other words, you have to verbalize, right, your conclusion. What does that mean in the context, within the context of your problem? Okay? So in order to get perfect score in the exam, you have to do all these 6 components. Okay? All right? All right. Any question so far? All right, so here's an example. So somebody claims that the average number of TV sets in the American homes is 3. And let's say we know the population standard deviation in this case. Let's say it is 0.8, right? Then how do we run this test, right? So you have to set up the null and alternative hypothesis that way, okay? And suppose you decide to use 0.05. Well, obviously this is a two-tailed test because the null alternative hypothesis says not equal to, right? If it says either less than or greater than, then it will be a one-tailed test, right? So if you decide to use 0.05 as alpha level, then you have to distribute half of that on each side, right? So this will be the situation, right? You'll have 0.025 set up here as the rejection region, and another 0.025 here as the rejection region, right? And you have to calculate the test statistic, Z. Okay, let me follow the steps here. Okay? So determine the appropriate technique. Because sigma, population standard deviation, is assumed to known, right? So you have to use z-test, right? And since alpha is 0.05, right? You have to find a critical value from the z table, and you find out it's 1.96, right? Do you need me to do this? How to use z table? I didn't bring the z table with me today. Yeah. Well, we have about 5 minutes until my assistant comes in, so I hope she remembers. Okay, let me see. Okay, this is a typical z table, and there was a very primitive z table, right? So the way you use the z table is, suppose your z-score comes out to be 1.28, right? Then here you locate 1.2, and then these numbers are the numbers on the second digit below the decimal point, right? So if you have 1.28, then you have to look 1.2 here and go all the way across to 8, right? So that number is 0.1003, right? So what that tells us is when we have z table or z distribution, okay? If you have 1.28, right? And then the size of the area outside 1.28 is 0.1, almost 0.1, right? 0.1008. Okay? So if you have negative 1.28, right? Then that's another 0.1008, right? So the area between these two numbers is almost, what, 90%, 80%, 80%, right? Something like that, right? So, what would, suppose you want to use alpha of a 0.05, right? Which means alpha, half of alpha is 0.025, right? Then, first of all, inside the table you have to look for 0.025, 0.0256, 0.025 right here, right? 0.025 is 1.96, right? You see that, right? So if you have the z-score and looking for the area, then you can start out from the margin, right? And look for the z-score, and these numbers are area, right? Size of the area. But this time we are doing the reverse, right? When we decided to use 5% as the alpha level, right? So on each side, if you're running two-tailed test, we need to set up 0.025, right, on each side. So what will be this z-score, right? And we find out it's 1.96, right, from the z-table. That's how you use the z-table, right? Okay. So here, set up the critical value and set up the rejection region, right? And then based on the actual number of sample mean and the sample size, you can calculate the test statistic. Test statistic in this example came out to be -2, right? So here we have critical value of -1.96 and +1.96. But the test statistic actually is found here, right? Inside the rejection region, right? So the conclusion is reject the null hypothesis. And what that means is that we have sufficient evidence that the mean number of TB sets in the US home is not equal to 3. Okay? All right? Good. Any questions so far today? All right.